AB Calculus Note Card 1, Average and Instantaneous Speed. The note card system was developed with the help of others by Stacy McMullen, formerly of the Dallas Independent School District. I have been at 2 summer training sessions with Stacy and was also mentored for 2 years by mentor associate Tracy Etheridge in the school district, and so I have a fair amount of experience. I want to give credit where credit is due. And here is and the reason I call this a note card system, because originally these principles were actually on note cards. So here it is, average and instantaneous speed. The average speed is defined by the total distance traveled, d, divided by the elapsed time period, t. And graphically, the average speed is the slope of the secant line, and so you have the absolute value of the change in the distance over the change in time. Instantaneous speed is the speed at a specific instant in time. Graphically, the instantaneous speed is the slope of the tangent line at a specific point. Analytically, we need calculus to determine this instantaneous speed. And so we're going to go through an example of that, and the example we're going to use is by using a roller coaster. And this is a roller coaster that can be set up sort of like on an XY coordinate plane. So if I set this up here, an XY coordinate plane, this part of the curve, and we want to find at a certain time, okay, time C, we want to find the slope of this tangent line. We can find the slope of that tangent line, or estimate it, by taking points on either side and evaluate the slope of an average rate of change, and then get points on either side closer and closer. And what this does, it's through what we call a limiting process to hone in on what the instantaneous rate of change is, or the slope of this curve at this point. And here we're going to go through an exercise to show that. And this says calc, means the calculator problem. A roller coaster has its largest drop modeled by the equation d of t equals 1.93 t cubed minus 31.82 t squared plus 113.83 t plus 158.65, where d of t is measured in feet and time t is measured in seconds. What is the average speed of the roller coaster from 2 seconds to 8 seconds? Well, what we do for that, our average speed is going to be the change. So we're going to have, we'll call this B, and we'll call this 2A. So our average rate of change is going to be d of B minus d of A over B minus A. In this case, we're going to have, I worked this out in the calculator previously, we're going to have d of 8 is equal to 20.97 minus 274.47 over 8 minus 2. And we work this all out in the calculator, we get negative 42.25. Well, to find the speed, if we go back to we see this absolute value of change, and so our absolute value is going to be just 42.25 0.25. In this case, it'll be feet per second. And then we're asked the question, what is the average speed of the roller coaster from 4 seconds to 6 seconds? Well, again, I worked this out previously. We're going to have d of 6 minus d of 4 all over 6 minus 4. And for that, we get 112.99 minus 228.37 all over 6 minus 4, which is 2, and that's going to be equal to negative 57.69. Okay, and that's going to be 57.69 feet per second, speed anyway. Okay, so, and what we have is we have a limiting process, and what I did is I also got a little closer to, you're trying to hone in on 5. I got a little closer to that. I used 4.9 and also 5.1, and for that, our average rate of change, and I'm going to just write what the answer was here for that. I got negative 59.6007, which the absolute value is going to be 59.6007. And so what we're doing is, through limiting process, we're getting closer and closer to what the instantaneous rate of change is. As we get infinitesimally close, we have the instantaneous rate of change, and that is really what differential calculus is about. And it so happens I did figure out what that instantaneous rate of change is, and the correct answer, and I had to use calculus for that, just like they said, was going to be 59 point, took it out several decimal places, 61999,807. Okay, that's out to the 10 or 100 millionth place. So it's a limiting process, and that's how we will, this is sort of a preview to differential calculus. Good luck, and thanks for viewing.